afternoon session. The first speaker of the afternoon session is Melissa Liu from Colombia, and the title of her talk is Open Relative Correspondence and Topological Recursion.
Oh, thank you very much. I wish to thank the organizers for the opportunity to speak here. I have learned a lot from these two workshops. So let me start with something very general. So let's consider some general problems. So this is say this is a projective manifold, complex manifold. So in this case, omega is the C1 of some polarization, or more generally, so where omega, this is a compact scalar, or even more generally, so this is symplectic form and this is a complex structure. We can more generally assume it's just almost complex, but today I'll mostly just deal with projective or quasi-projective manifold. So then, so I would like to talk about Gromov-Witten invariant, open Gromov-Witten invariant, and relative Gromov-Witten invariant. So let L be a Lagrangian submanifold. So D is a divisor. So it's a projective divisor, or in this setting, just a symplectic divisor. So we can consider Gromov-Witten invariance of X, so fix some so this is enumeration of C. This is genus G to X, such that which is an effective curve class. So open Gromov-Witten invariants of XL G so we consider, so before we compactify such moduli space, we consider holomorphic maps from a border Riemann surface of genus G, and with M boundary circles. So this is so here the topological type of domain is characterized by G. So here's G and N. So then the topological type of this map so the fundamental, so we push forward and we get a relative homology class. So it's the domain is oriented by the complex structure, and the boundary circles has the induced orientation. So we know what this is. So this is some mu I. So right now mu I is an element in the first homology class, and then there's a boundary map, and this should be compatible in the following sense. So also we consider relative invariance. So this X relative to D so F X, so this is genus G degree beta. So we require that if you pull back this Cartier divisor D, it's given by, so now here this mu is a partition. So here each mu I is an element in this group, but then here this mu I are just positive integers. here x1 to xn are distinct points. On the domain. So of course, if we want to define this, so for this we use like conservation, stable computification, and then also there's a relative version where you need to introduce node on the domain, also allow the target to bubble. So under these assumptions, the Gromov-Witten invariants of X and relative Gromov-Witten invariants, so these are well established. So in the algebraic setting, so there's this, so these invariants are defined by virtual fundamental class on the moduli stack of genus G degree vector stable maps to X, and also there's a relative. Oh, sorry, n is something else. So L is the number of marked points on the domain. Right. So these are proper Deligne-Mumford stack, which are usually singular but virtually smooth, and there has been many constructions of these virtual fundamental classes. So, but the problem is this thing, open Gromov-Witten of XL. So this is like, yeah, this is usually not well defined because of the following. So you can consider moduli of this map. So L is the number of interior mark point, and now we have m boundary components. So let's say the boundary components are ordered, and each boundary component has certain number of mark points. So this, even after like the stable computification similar to this is like singular orbifold with corners. Yeah, so this is some problem. And also this moduli space are complex and canonically oriented. So this is not always oriented. So it is virtually smooth, but it's not complex. You see, even if it's actually smooth with these corners and boundaries, hard to do intersection theory. So what I want to do is today to give you some very special cases where some open Gromov-Witten invariants which arise in the topological recursion. Because this topological recursion, we need to define it for all genus. So in some special cases, we have this. So for pair XL, so we can construct another pair, so this Y, which is not necessarily the same as X and D. So this pair is the same, such that we can argue that this two should be the same. And then, so this is well defined and canonically oriented. Okay, so maybe, so yeah, so that's, I'll show some examples. So so
yeah, microphone is probably inside your.
Is there a possibility to turn off the group
Oh yeah, I think.
Maybe now it's okay. It was
shirt. And then the shirt was
No, I know, but it's the general phenomenon.
A general. Oh, so is
We
it?
just see this in here, right? So
It's okay now.
It's okay.
Oh, it's okay now. Yeah. So sorry. So the first is like the most Hurwitz problem. So now so now G is mu1 to mu(n). So this is a partition of some positive integer d, where each so maybe first pretend we don't know the open and relative are equivalent. So there's open version. So this should be count. So this is genus G. Oh, is it still bad? Sorry,
Maybe can you turn off the volume?
Yeah, it's still in the record too.
Well, no, you can record it,
Yeah.
but without transmitting it.
But yeah,
Yeah. But of course, you should be careful. It doesn't still work.
so F sigma is okay. So let me draw a picture here. So this is P1 and a circle. So this is an open. So in this case, X is P1 and L is a circle. And I just want to consider, so this is beta 0, and this is the class of this circle. So we want this to be so we want the simple branch points. So we fix branch points, and we want to count like the weighted count of such cover is this Hurwitz simple Hurwitz number given by this genus G and this ramification profile. So these are here Zi are distinct point in the here. I'll just draw it like in the interior of this upper the hemisphere. So the relative problem is, so you see we can, so this is like very classical, right? So this answer is expressed in terms of like the transposition, like purely combinatoric, and Burnside already solved this and much more generally. But we can also just use this very modern approach, and then we run into some difficulty because of the problem of this moduli when X is P1 and L is a circle. But then the thing is, in this problem, I want to say that in this problem we can consider this. So now it's P1 relative to, so this is the degree D. And then we want the pullback of infinity is so x1 to xn, so distinct. So the branch F is Z1 plus ZR plus D minus N infinity, where Z1 to ZR are distinct point in. So yeah, combinatorially, this is the same combinatoric problem. So this is and also the Burnside formula gives you it's So you can consider the disconnected version, where one allow the domain to be disconnected with Euler characteristic 2 minus 2g.
It looks like you consider not one divisor but several divisors, because each multiplicity tangency will be with different divisor, yeah, like when Z1 or Z2, Zr. In relative situation as well, yeah.
So relative, I'm just saying that. So now it's just one. In general, the Hurwitz problem is the target can be any genus relative to several points. For each point, So it's much more general. But this is a special case. Actually, I think. Danilo is going to talk about the very general Hurwitz problem in his talk today. So, but this is just a special case of what he will say. Is this okay? Yeah. So this is a simple Hurwitz.
No, but in general, I think for relative things, you can assume that you have not just one divisor but many divisors.
Oh yeah. I will have many divisors. So yeah, maybe. Yes. But today my divisor can be disconnected by smooth, but no more crossing.
Okay,
Yeah. So here, right? As you. I think. Sorry, I'm slow. I think you mean that this kind of correspondence still holds if we replace P1 by a higher genus.
No. Several. It looks as here you just get different conditions, different kind of touching conditions goes to different divisors.
Yeah, right. So now you can relative to several.
Yes.
Several. So actually there's this Burnside for okay. So maybe okay. Let me first write down this generating function. So I think Burnside formula is you fix this, and this U is the genus parameter, which was also appeared last week. So you can consider G sum over G. So fix this ramification pattern and sum over the genus. There is a generating function. So this is by Bern. Yeah. So as Maxime pointed out, actually the Burnside formula is applicable to much more general setting where your P1 can be replaced by a higher genus curve, and then you can relative several points. So you will have several. So then there's this also has this Burnside formula, and even more general. So this can be we can consider X relative to like Q1 to QK, right? So this is very special. Yeah. Okay. So.
What do you mean by a Burnside formula? The character formula?
The character. Is how should I
call
it?
It's absolutely
That's how you
symmetrical.
Right.
Oh yeah.
That's idea.
Yeah. Right. So, but then now that's okay. This is very combinatorial. We know they are the same enumerative problem. But now we can try to do this in a more difficult and rigorous way by using relative. So actually we can consider so this is P1 relative to infinity specified as G and mu. So this is the stable compactification of this. So here, so a map like this. So to do this relative compactification, so this is the original P1, this is the original infinity. One needs to allow the target to bubble, and this is the Q, and there are M copies. And then So there's matching condition. So for each of this node, the pre-image is a bunch of nodes, and the contact order needs to match so that you can smooth it back and get some map in the smooth domain. And we require that this. So this is F0, F1 up to Fm, and this is the whole domain C, and this is P1M. P1 added a chain of bubbles, which so this is so each of this has degree D, and then one can consider, so over this, moduli space, so there's this universal domain and universal target, and then universal ramification divisor. And then this universal copy can get a contraction to P1, and then let's call this F tilde, and then so then we can consider the branch. So we can so take this part. So this branch divisor. Yes.
So you don't have a condition of stability when you do this.
Oh yeah, I have stability. I apologize. So yes. So I should say one or two such maps isomorphic. So two such maps are isomorphic if so first the target must be the same number of bubbles, and here you can mod out this C star M, and so this F and F prime, and this is the isomorphism of the domain fixing the mark points. So this is the isomorphism between two objects, and the stability condition is the automorphism group is finite. Yes. So yeah, okay, so this is, okay, I should do this computation. So this is the other mark point, so this is, one can compute is 2G minus 2 plus D plus N, where D is the size of mu and N is the length of mu. So then this, so then actually this H, so this is actually a morphism from this usually rather singular stack to an r-dimensional projective space. So this singular stack has a virtual dimension equal to this R, and then this very classical, if you so we do this simply because here in this modular problem the xi's are ordered, so that's why we need to divide it by this. So yeah, this should be like the degree, right? So now so there's this more difficult definition. So of course you can also but there's also a branch morphism on this. We don't know how to define the virtual class of this, but there's this P1S that's also S circle mu, and then after we compactify it, it has a branch morphism just like symmetric product of the closed disk. So you can see clearly that it has corners. So but then there is a way to, but now the thing is this can be computed by, so there's a circle, action on the target. It induces fixing this point, and it induces, so we have a circle or C, so let's just use the circle action. There's this infinity, and then we can actually choose a particular point so this is the normal bundle of this fixed locus in the whole thing, and so I want to take this point, which is just, so this branch divisor is just r times the 0. So this is fixed by the torus. This is one of the fixed torus, a circle fixed point in PR. So the advantage is if you use this particular torus action, then actually, so when the target has bubbles, it doesn't contribute. So the only thing which contributes, so this becomes MGN, and you just have this. So this is degree mu1 to mu1 cover, and this G to G. So then after localization, one gets this ELSB formula. Okay, I hope I didn't remember this wrong. So, but then we can also pretend that this works. Now we can just pretend. I mean, we don't have a virtual fundamental class, but then we just put this moduli and we start from here. So what we get is the following. So then. So if you do the same computation here, you get almost identical. You also get some, yeah. So basically you get up to a sign, you get the same formula. Yeah, I think because here the fixed point is this, so actually, so the fixed point is also, so this fixed part is also a copy of M bar Gn, and then yeah, up to some automorphism of this bubble. So this is an integral over M bar Gn, and yeah, 0 is inside the disk. So then up to a sign, which depends on how you orient this moduli space, you get the same formula. So yeah, so my strategy of doing open Gromov-Witten invariants on this in this context of Lagrangian duality or topological recursion is we observe this and then we choose a torus action on the relative moduli space such that these are almost identical up to sign. But here the moduli here is actually yeah, canonically oriented and has a definite sign. Okay, so that's the classical case. So next case is actually we want to apply the same strategy to this topological vertex. Maybe let me call this E, and then there's an involution. So if we restrict this to, so if we restrict it to the one chart, so there's an involution from the total space. So if we use the affine coordinate as this, so that's fixed. So this is sigma and tau. So this is Z. So in the base, the equator circle is fixed. Yeah. So now let's so that L be the so this is just a rank 2 trivial vector bundle over this circle. So now the picture is like this. We have and I also want to count. So now we replace this by since this is homotopic to P1 and S1, so we can just still count the multiple cover of this, but now there will be an obstruction bundle from this, and then actually it turns out that we can also degenerate this picture, so we get so here this is a open version, but then we degenerate this picture. So now it becomes O minus 1. So this becomes, so this is O minus 1, O minus 1. It degenerates to O minus 1 over a half. So now relative to this point. So now, actually, so now we can
things over 0 infinity, it's like coordinate axis in the fiber bundle.
Oh, so yeah, so this, sorry, so this.
You mean these cones kind of on the right to the left, which you put it in 0 to infinity?
Oh, sorry, yeah, I think so. So here, so this is the.
This is CP1, yeah.
Yeah, this is CP1, and this is fiber over 0 and fiber over infinity.
Right,
These
right,
are.
it's the two cones. Yeah, it's a C square.
Yes, C square. It's it's C. So
real picture, complex picture.
Yeah, I'm sorry. I wanted. Okay, yeah. So but then if you have the moment map picture, and you can put your. Yeah. So that's the picture.
Okay.
Yeah. So then actually so.
Torus orbit.
So okay. So I should say that there's this framing. So the thing is like. So now. So this vector tells us how you degenerate O minus 1 plus O minus 1. So when I draw it this way, it's like O and O minus 1, and here's O minus 1 and O. So then you look at, so after degenerate, so what, so in the absolute case, you have some obstruction bundle over, you need to integrate over M bar GP1D. So now, so this will give you some obstruction bundle. So yeah, so now we want to say that in this case, because in this case, H1L is the same as Z. So previously, so this mu is really just can be viewed as a partition, and so I won't say that, yeah, so this gives us obstruction bundle that means say G mu, or the rank of Bg mu is the same as the virtual dimension of basically so if you have so maybe it's easier to, so if we have some map to P1M, so and then so this is the ramification divisor, then so okay, so this is a point here. I'll just describe the fiber. So this is O C minus R. Yes, so then H0 is 0, it's a bundle. And so then if you, so then actually, so one can use different torus action to evaluate this integral. So we want to use so W1x on the base, W2x on the fiber of and then so we will get some following. So we can, it will be convenient to consider some disconnected version of this. Yeah, disconnected version of this. So it's so then you see the disconnect, because now in this relative, actually you see the fixed locus is the same as the previous problem. So it's, so what happens is you have something here and might have some bubble here. Yeah, actually. So here we have the partition nu, and in the middle you have nu1 up to some nu k, so have some partition nu, and this is possible disconnected. So then, so here you have nu. So So you form this generating function and you do the localization. So on the left-hand side, you will get some generating function of triple Hodge integrals. And then on the right-hand side, you will get some like generating function of disconnected double Hurwitz numbers. So this is by localization, but then this double Hurwitz number. But this actually tells us. Yeah, so this gives us the framing dependence. And moreover, because of this framing dependence, actually you can replace. So now I want to, so this framing, so now I want to actually consider, so this W1 to W2 is, so you see, if I want to get some rational number, I can specify a one-dimensional circle in here, then I get a rational number. But you see this, so this G, this is open invariance. It depends on the circle action. So this, if I do the relative thing, the whole thing doesn't depend on the circle action, but the contribution from the part where the target doesn't bubble depend on the torus action, and is up to a sign what you get when you localize on this moduli space. So now I want to actually yes.
So this G is just generating series of triple Hodge with parameters W1 and W2.
Yeah, yes.
And what is this Z?
Oh, this is I think this is mu1 to mu n, like automorphism. So yeah. Yes. Double Hurwitz numbers. Yeah.
Lambda implies to be U.
Oh yeah, it should be you. Sorry, I changed the notation this morning. I apologize.
And also the torus weight at the infinity of the torus diameter. So
Oh yeah, this is W2 minus W2. Thank you. I apologize. Okay. So but now you see that the roots. So now if you instead do so this has the following consequence. So if now you change this target to this one, so this becomes so now if you choose so the thing is now if you specify to the subtorus, which is so if you specify the subtorus, so when this weight is 0, then your target so there's no contribution from the bubbles. So actually, so then you can actually say, so then actually what I want to say is the following. So this is an example of this. So we want to, so this is like, so when you specify this to W1 over W1, W2, W3 to this weight, so I want to say that this open Gromov-Witten invariance, so this is C3 with L. So now this is defined by equivariant localization and depend on this weight. So this is relative Gromov-Witten invariance of this YF DF. So this, so you consider the moduli space. So where YF is the total space of OF O minus F minus 1 over P1 relative to infinity. So so these two are equal by the localization. Moreover, if you, so a priori, because this is not a vector bundle, so a priori, if you just do localization on the total space, the answer you get should depend on the torus weight. But actually, because of all this calculation, it turns out that you can specialize to any weight, and you will always get the same answer just depending on F. So now this has, so yeah, so this is because when we have link, so for example, so in large N duality, if you have a link with several components, so the answer is you should be able to vary the framing independently. But then, so this, under the line, so this is the frame mirror curve. So this will give us Gn C3LF. So the open invariant depend on the framing in this way, and because the framing is a choice of circle action, so if you have, so if you want to do 3 Lagrangians, so from the, so this is related to the color home flip polynomial of this, and here you can vary the 3 framing independently. But if you just use this, you cannot. But actually, but then our strategy is the same. So you consider a formal neighborhood of these 3 axes in C3. So now we replace the Lagrangian by a point. So this comes, so a point, but this comes up with the ambient space. So this point actually corresponds to like the formal completion C2 at the origin. But when you do this, when you add this point, you need to specify the normal bundle. So this O F1 plus O minus F1. And maybe I'll just say. So this, I have this F1, F2, F3. So I get a pair F1 depending on the framing, and I also get D1, D2, D3. So yeah, now actually we have 3. So now we can consider this. So, and we do the moduli space of relative stable mass. So in this moduli space, you have all these bubbles.
Is by compact?
No, not compact. So a priori, when you localize, your answer should depend on not only F1, F2, and F3, but also the equivariant. Yeah. So, but then like John Walker, Jimmy Liu, and Jianzhou a long time ago. Oh, Jianzhou cannot come because. So the theorem is, so if we consider the relative so this is so a priori should depend on. So this is actually in Q if you choose the Calabi-Yau weight. Of course, after you prove this, after there's this other so the Maulik of Oblomkov, Okonkov, and Panda, so they also related to the DT vertex, but that's difficult. But once you relate it to DT vertex, this is also clear because there's a Serre duality, and this is like canonical line bundle is equivariantly trivial. So then this, so then this doesn't depend on this. So then we have this. So this is also implies actually if you consider the. Yeah, if you specialize to this Calabi-Yau torus, but if it's like 3 parameter, then it depends. So this also, because then you can, for any tori Calabi-Yau threefold, you can degenerate the one skeleton, and then, so this will imply that, so this is defined by this. No, actually, this is just by equivariant localization. So, for example, if it's so this is any tori Calabi-Yau threefold which is non-compact. So the thing is, this does not depend. This will be a rational number if you specialize to the Calabi-Yau torus.
So what is the statement of the theorem that this is?
So this is actually because this this is when you actually so this is computed by doing localization on like relative stable map to this YF relative to this 3 divisor, but because this YF is just a formal completion of this 3 P1s. So this moduli is a formal scheme. It's just not proper. So if you do localization, it should just depend on the equivariant parameter. And actually, you can do it using if you use the 3-dimensional torus, it will depend on the equivariant parameter. But if you use like 2-dimensional torus, it should a priori should depend on the slope, but it does not. So this is the theorem. So as a consequence, this also doesn't depend on. Yeah, this is okay. Maybe it's some. This f is different. This f is like the slope. But now there's another proof, because once you know that this is given by the topological recursion, so to yes, sorry. Yeah, thank you. Sorry. So this is yeah. So the open invariance will depend on f, but it's a consequence of the because the b. Because this omega g0 actually does not depend on f. So then after one proof this, it's another proof that this actually, using the Calabi-Yau torus, this actually are rational numbers. So now we also, So now the thing is, now we can, so in the orbifold case, so in general we cannot prove something like this. But then we prove that, so then so this is X is Calabi-Yau manifold. This X is Calabi-Yau orbifold. So yeah, so now we can actually, so now like this framing is more complicated because this can be orbifold curve, and then the three axes are not symmetric. But similarly, we can also have this relative open correspondence by localization, and the relative moduli space gives us canonical orientation. And so we use this to define higher genus open invariants and prove that, and prove the remodeling conjecture. So then in this case, it's a consequence of this proof that FG X so this is some extended Taylor parameter. So this is doesn't depend on like this slope. Yeah, so okay, so actually, so now there are some these cases is when this can relative open correspondence work in this case. But the case I want to do is, for example, for in the resolved conifold case, if you have Lagrangian, which is actually coming from the large N transition of the conormal bundle of a knot in the cotangent bundle of S3, then it does not have any circle action and you cannot compute it. But this Lagrangian still has the topology circle times R2. So I hope we can do a similar construction, just modify it depending on the Lagrangian knot and the framing, and have a divisor. Then we have definition of relative invariance. And yeah, at least the framing dependence will correspond. Okay, thank you for your attention.
Questions, comments?
How you will complete orientation?
Oh, so actually in this case it's because if we so if we look at the, so if we localize it, we look at the so in here, so there are fixed locus. So there are one part of the fixed locus correspond to the part where your target is just this no bubble, and that is up to a sign essentially equal to you do localization on this moduli space of in open Gromov-Witten invariants. So this is canonically oriented, so we use the orientation coming from here.
Any questions? Otherwise, let's thank our speaker again.